Okay, let's have a quick look at this question together then. A physics teacher demonstrates refraction of water waves in a ripple tank. This is a difficult question, a higher tier question. Complete the diagram to show the wave fronts in shallow water. So this is about refraction. Refraction happens when waves change speed. There's a change in speed, and that causes them to change direction. Now we know from the waves practical that waves travel faster in deep water than shallow water. So what's going to happen here to the speed? The speed's going to decrease, they're going to slow down. And what will happen when they slow down is you'll notice the change in direction, first of all. So they're going to do that sort of thing. Try and keep these purple ones, the waves in the shallow water, try and keep these parallel, that's important. I'll draw another one there so it makes a bit more sense. They're parallel, and the space between them, which is the wavelength, is staying the same. So there we go. So whereas the direction arrow, which is at right angles to the wave fronts, whereas it's going in that direction in the deep, in the shallow, the direction is going to be more like that. That arrow isn't needed actually. The question only asks you to draw the wave fronts. We've drawn the wave fronts. Okay. The wave generator in the deep water produces 5 waves in 10 seconds. Use an equation from page 2 and a measurement from the diagram to determine the speed of waves in the deep water. Now the equation that you need is wave speed equals frequency times wave length. You can pause and look that up. It'll be on page 2 of your exam, or it's the inside front cover of your book. So to work out the speed, we need a frequency number, we need a number for that, and we need a number for that. We're going to times them together. Now you can measure the wavelength. That's what it's saying. Look, measurement from the diagram. It's the wavelength we can measure. And before we do this, I just want to point out the fact that the speed, they want the answer in meters per second. So we're going to need to make sure that the wavelength we use in meters. Slight problem. Now, this sheet that you've got has been reduced, so it's not the same size as it would be on A4. I think if you look in the mark scheme, they measure this to be 1.4 centimetres. Ours is obviously not quite that, is it? It's more like 0.8 of a centimetre. All right, so let's see, wavelength. It's 0.8 of a centimetre. What's that in metres? How do you turn centimetres into metres? Divide by 100. So it's 0.008 of a metre. Okay, so that's our number we're going to need for wavelength. What about the frequency? It doesn't tell us a number for frequency. We're looking for a number in hertz. But what it does tell us is this. What you need to remember is the definition for frequency. Frequency of a wave is the number of waves per second. That's your definition. And it does come in hertz. Right, so if we have 5 waves in 10 seconds, how many waves in 1 second? If there are 5 waves in 10 seconds, 5 divided by 10 will tell us the frequency. Don't need to do this on a calculator really, do I? 0.5 hertz. Okay, so now we know a number for wavelength, a number for frequency, and we can use this equation. Speed equals frequency, so what's my frequency number? 0.5 times my wavelength number, 0.008, which equals 0.004. 0.004 meters per second. Okay. For this one, look it in your notes, but frequency stays the same. The speed, going from deep to shallow, the speed decreases from deep to shallow. And wavelength decreases, going from deep to shallow. Okay.